let's begin as a two-grid scheme. A multi-grid usually stands for more than two grids, right? But let's draw a two-grid scheme. So the first step is smoothing. That is to compute my xk. And smoothing is important because it ensures that solution error is smooth, and your Coarser grid is capable of representing the solution error. So without smoothing, multigrid doesn't work at all. Or if you don't do enough smoothing, you find multigrid can diverge. Okay, so the second is residual. RK on a Coarser grid. So here I want to emphasize that you can't just look at the residual from a linear algebra perspective. You have to look at the residual on the differential equation perspective. Like dashes all the time. Okay, yeah, you have to look at it from a differential equation perspective. So for Poisson's equation, my RK is actually equal to my right-hand side minus the Laplacian of the solution x. Because here, what you are doing is you are going to be representing this on the Coarser grid. And in a linear algebra sense, there is no, like, you can't really say what is a Coarser grid, right? You have to be able to interpret the residual from a differential equation point of view. That's why multigrid usually applies just to differential equations, right? Usually when you have, for example, if you have a coupled system, you have a PDE and something else that is not a PDE. Coupled, you have a huge linear system composing different parts. Multigrid usually in that scenario serves more as a preconditional. So you don't simply rely on multigrid to solve the whole thing. I'll talk about preconditioning a little bit later. So you have to interpret R as a field variable and restrict it to a Coarser grid. So this is called a restriction. And the third step is to solve delta xk, a delta xk equal to rk. Usually approximately, right? Because even on the Coarser grid, it is usually not feasible to use a direct method. If I have a grid of 4,000 by 4,000, even a reduced grid is 2,000 by 2,000. So I use the iterative method and solve it approximately. And 4 is that now I solved this, right? Okay, so this A, I think I should denote for A tilde because it's actually not the same A, right? Even the size is different because I'm on the Coarser grid. So this A tilde is a discretization of the same differential equation but on the Coarser grid. So that's another reason why you need differential equation to apply multigrid. It's not just a simply linear algebra manipulation. 4 is now you have delta xk on the Coarser grid. You have to add it. So you have to add this delta xk, but they are not the same size. So you have to interpolate this delta xk from a Coarser grid to a final grid. You have to fill in the grid points that is not there in the Coarser grid. And this is going to be my next a better solution, right? So it is not exact because of two reasons. One reason is in step 3 you only solved approximately, and another reason is that you cannot represent the delta x exactly on the Coarser grid, right? Even though the solution is smooth, but like you are still only representing the solution error approximately on the Coarser grid. So this is going to be an approximate, but this is going to be my this is going to be a much better solution than I started with, and I'm going to feed it as an iterative loop. So then the next thing is I'm going to have the whole thing as an iterative loop, right? So that's what multigrid is. And an optional step 5 is before you return the solution, I'm going to apply smoothing again. Because the interpolation depends on what differential equation and what interpolation scheme you use. The interpolation can actually introduce oscillations, and the smoothing just takes away these oscillations. So step 5 is optional, but step 1, the smoothing, we call pre-smoothing, is mandatory, because otherwise you cannot represent the solution area on the Coarser grid. Okay, so then this is the iteration. So as we can see that multigrid is actually a loop within a loop. So the outer loop is the multigrid loop from 1 to 5. And the step 1 and step 5 actually involves a loop by itself, because it is applying the smoothing. Usually applying Gauss Seidel just for one iteration is not enough to smooth the solution to sufficient smoothness so that it can be represented on the Coarser grid. Right, any questions on this? Yes. That's a good question. How is 3 solved? So 3 is solved potentially in 2 ways. So if the coarse grid is coarse enough so that your iterative method, so first of all, if the coarse grid is so coarse that, let's say it's a 2 by 2, you can backslash, you can directly solve it. And 2 is when your coarse grid is coarse enough, but not that coarse, but coarse enough for your iterative method to converge sufficiently fast, let's say 100 iterations. And doing 100 iterations on the Coarser grid is usually nothing compared to the full grid. Then you can just do that. The third option is actually that's what we have in our case. If we have such a large grid that even the Coarser grid, we have a very slow convergence of iterative method. Then what's the solution? Multigrid again, right? That's why often multigrid in a computer science term is a recursive algorithm. So in order to, so let's say if the whole thing from step 1 to step 5 is called a multigrid cycle. Multigrid cycle. Step 3 usually involves 1 or 2 multigrid cycles on the Coarser grid itself, right? So it's actually interesting to envision what this program is going through, right? So let's say if step 3 involves 1 multigrid cycle on the Coarser grid, then what happens is that there is going to be a hierarchy of grids, right? So from the finest, let's say n equal to 4096, n equal to 2048, n is equal to this, and 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 this. Okay, usually it doesn't make sense to go all the way to 1 by 1 because everything is boundary condition. Okay, so what I do is I apply step 1 here, right? I do the smoothing here. And step 2 goes in between these 2 grids, right? And step 3, which is, the whole thing, which is actually a recursive solver because it recurs itself. So let's change the color. So the whole step 3 is going to be over here, right? So let's say this is step 3. It actually involves calling step 1 again from the beginning on this Coarser grid and the step 2 between them. And then let's change even another color. Then the whole thing is going to be step 3 on this grid. So basically I call step 1 again, step 2 again, right? So basically I go all the way to the bottom 2 by 2 grid. Once I'm a 2 by 2 grid, I can just do direct solve, right? Because there is how many unknowns? 1, right? 1 unknown, I do direct solve. And then I go backwards up to here, right? Well, okay, so sorry. In the bottom, let's imagine 2 scenarios. One scenario is when we when each step 3 just involves one multigrid cycle on the Coarser grid, then we are going backwards all the way, right? And then at some point, we'll be calling step 4 and step 5. Then step 4, step 5. I should be using these colors better. So step 4, step 5, and then back to the red grid. Step 4, step 5, and then back to the green grid. Step 4, step 5. Right. So this is what's involved in a multigrid cycle, and because the shape looks like a V, it's called a V cycle. So V cycle, multigrid, is basically step 3 is one multigrid cycle. Does it make sense? Okay. There is also a W cycle. So as you can imagine, what if my step 3 is having 2 multigrid cycles on the Coarser grid? Then the shape is going to look pretty much like what you see in a fractal picture. So it's something like you go down, you zigzag a little bit, then you go up, zigzag a little bit. Okay, now you go up again, you zigzag, you repeat the pattern. Now this time you go up further. It's very hard to draw consistently, but this is what you have for a W cycle multigrid. So basically, the higher you go, the less frequent you are iterating on this grid, right? And W cycle is very popular for 3-dimensional problems because as you go down, the amount of work is so much less. All right. Yes.
You have to plan how many points stuff into actual cycle down.
Yes, you have to plan how many grid points you have on your mesh. So you either, right, if you can do that, that'll be great. If it's a factor of 2, if it's a power of 2, that will make your code very easy to implement. If it's not a factor of 2, then in some part of the code, like in the interpolation and restriction, basically you are going through, you are interpolating, or call restriction, the residual from the fine grid to the coarse grid. And then you are going to be interpolating the solution error, called prolongation, interpolating the solution error from the coarser grid to the fine grid. Right? These 2 steps is is very easy to do if you have a power of 2 grid. These 2 steps would no longer be so trivial if you have an arbitrary